Boom. Hello and welcome back to Calculus 3, section 14.3 on conservative vector fields. The last time when we talked about vector fields, we said that the vector field is to be imagined as a whole bunch of points in space, in 3D space, and each point in that space has a vector associated with it. And there is a vector equation that it's a collection of functions that would calculate the vector, which obviously has its direction, has its magnitude, and everything else. And then we said the easiest way to visualize vector space would be to just think about the wind, or right. So you have the fan like this one above our heads that it's constantly on, and it's pushing air. Right, the fan is pushing air. So each air particle will have some kind of a velocity and motion through space, and that can already be represented. Each individual particle can be represented by a vector, its motion, and so on. So now we also said that why ping? That the vector field f will be a collection of functions f, g, let's say age in 3D, and so on, right? Now, we also have, I'll put old, definition for R, which was vector valued function in general, which had f of t, g of t, and age of t. Now that's collection of functions as well. Another thing that it's old is if you have that the function of xy, z is given as a function of xy. So now when you put all of these concepts together, you realize that if you take the gradient of a function, let's say, I don't know, whatever, function g, no, can't use g, can't use any of these. Well, we use phi. We get partial derivative of x, partial derivative of y, partial derivative, let's say, of z as a 3D. We can, and these are all functions over here. Since they're all functions, that means that this thing is a vector field. So the easiest way to generate the vector field is to find the gradient of what we call a potential function. So the easiest way to generate a vector field is to find the gradient of a potential function phi. Now, the interesting thing is that right? If you are able to take the gradient of the function and get the vector field, the interesting question is if you can actually develop a procedure which will allow you to, if you have a field, to figure out which function generated that field. And yes, you can do that, but only in a case when you have something that is called conservative vector field. So we will first have to figure out the test for conservative vector fields. So we'll see that conservative vector fields are vector fields, obviously, with a special property. When that property is satisfied, then you are guaranteed to have this potential function which generates that field. If the vector field is not conservative, you might not have such a function, right? So you have to be careful about that. So let's take a look at all of the things that we have. So first of all, we have this talk about types of curves and regions. These are definitions that you guys need to know. And I'm going to just give you the visuals. The text is given, so you can also learn the text. But so something like this, curve C, and something like this, curve C. So this is closed and simple. And this is not closed and simple. And then we have something like this, that it's closed, not simple, and something like this, that it's not closed, not simple. It shouldn't take long to see that closed means that one end of the line meets the other end of the line, and simple means whether it intersects itself or it doesn't. So when you say a closed simple curve, that means just the first picture upper left. None of the other things apply. Remember that you can do line integral on the ones on the top because the line needs to be simple, right? Now in blue, we're going to draw some regions. So this is region R, connected and simply connected. And another one with a hole inside, connected, not simply connected. Then we have not connected. But simply connected. And these are the regions, yes. And not connected and not simply connected. So, as you can see, the connected part means that it's one piece, right? The mainland, connected. When you have islands, they're not connected. And then you have a simply connected concept, which means that every line that you can possibly take in the region from point A to point B has to be in the region. Now, over here, obviously, this line that connects 2 points has part of it that it's not in the region because there's a hole in the middle. So that's the simply connected and not simply connected and what they mean. Our definitions from this point on will have these in them. All right, so let's go and define the conservative vector field. So a vector field F is said to be conservative on a region in R2 or R3, so 2D or 3D, if there exists a scalar function phi such that the vector field equals to del of phi on that region. And now we have the test for conservative fields. So these are the conditions. The f dy needs to be equal to the g dx. And then the f dz, these are all partial derivatives, needs to be the same as the h dx. And finally, the g dz needs to be dh dy. If you are using this one, that's only for 2D, so R2. If you are using all three, you are in 3D. So you have to remember all three. And you see that it's a combination first with a second, first with a third, and second with a third. They're just combinations of all. So all of the conditions have to apply in order for vector field to be conservative. If the vector field is conservative, then we have a procedure to figure out the original function which generated that vector field. So we are looking for potential function, right? And that's the goal of today. Remember the reason for it. You take a whole bunch of little sensors and you throw them into the hurricane or tornado or liquid that has a flow. And that gives you the data about the motion, velocity, whatever, of the vector field. You can do that with magnetic field, electric field, gravitational field, right? So you have a bunch of sensors which will give you a lot of data, and you know the vector field. Now, if that vector field, you express that vector field as equations, and then you check if that vector field is conservative. If the vector field is conservative, you can unleash the technique that we are going to learn now, and then that technique will give you an equation that governs that phenomenon. And that's how science is done. All right? So if you want to understand these kinds of concepts, right, you will have to know how to measure the vector field, and then to test the vector field, and then finally to extract the equation of the vector field. So now they have some of these practice problems. So what I'm going to do is I'm going to go into the homework, because the ones that you guys have in the text you can read on your own. I'm going to jump. Everything was supposed to open, did it? No, I'm talking chapters 11, 12, 13, and 14. Everything was supposed to open. That's why I asked, did it open or no? But the chapters 11, 13, and... What? Supposed to close on the day of the final. All right. Let's, unless someone has an Apple product. No, I'm not talking about applesauce. I'm talking about some of those stupid devices that you call computers and phones. No one? All right, fine. Whatever. So we're going to check for conservative vector field, and then we are going to start working on the procedure. I will do a 2D example first, and then 3D example. And we should have plenty of time to complete both. So problem 14 says check if the vector field is conservative. Now if it is, I will immediately transition into the procedure. So we have 2x cubed plus xy squared, comma, 2y cubed plus x squared y. Do you see that these equations are symmetric? Yeah? That xy squared is the same if you write yx squared, but we put x usually first. That's, you know, that's what symmetry is. Anyway. All right, so this is a 2D case. Therefore, all you need to check is the 2D condition. You only have one condition for 2D. And we know that the first one is our f, second one is our g, and we'll take these partial derivatives to check. So partial f, partial y is 2xy, right? And then partial g, partial x, partial g, partial x, also 2xy. So I'm going to put big fat green check mark, because we have the condition where partial f, partial y is the same as partial g, partial x. So condition is satisfied, which means that this is a conservative vector field. All right. So now we are starting the procedure to find a procedure to find phi. Phi is going to be phi of xy in this case, right? It's a function that has two values. All right, so where do we start? We pick either f or g. It doesn't matter. No, first what I want to say, let me write in blood over here. The f is phi x comma phi y. So that's a partial derivatives. So because this is a conservative vector field, right, we have that the vector field was generated by taking the partial derivative with respect to x and the partial derivative with respect to y. So that's what we have for our f. Now what I'm going to do is I'm going to pick one of the two. So I'm going to pick phi x, which is my f, which is 2x cubed plus xy squared. You see that the derivative was taken in respect to x, right? To get this. What's the opposite? The integrate x, yes. So I'm going to integrate 2x cubed plus xy squared dx. So when I integrate this, it's actually going to give me my phi. So when I integrate, I get 2x, so 2x to the 4th over 4 plus x squared over 2y squared. And now, guys, this is new, plus the constant as a function of y. You haven't had that before for integration. Why do I have constant in respect to y? Well, remember this was a partial derivative in respect to x, which means that y variable is a constant in the eyes of the partial derivative in respect to x. Therefore, over here, I could have number 7 like we had in Calc 1. But I could also have y to the 5th. And when I take partial derivative with respect to x, it's going to die just like it equals 7. So, we have to have function in respect to y over there. Now, this is already my function phi that I'm looking for. When I cancel, it becomes 1/2 x to the 4 plus 1/2 x squared y squared plus some function in terms of y. This is already an answer. However, we want to determine the constant part over there. Now, what I do is that I take partial derivative in respect to y of this. And set it equal to G, which was also partial of y, and that will give me cy. You see that? So when I take the partial derivative of the top in y, 1/2 x to the 4 dies. The second one becomes, so I'll put, okay, so 0 plus 1/2 x squared 2y plus c prime of y, because I'm taking the derivative. And that needs to be equal to g, and g was 2y cubed plus x squared y. So I took the partial derivative of the answer I got from integration in respect to y, and I'm setting that now equal to g, which is the partial derivative in respect to y from the vector function, from the vector field. Now, what I have is that x squared y plus c prime of y is equal to 2y cubed plus x squared y. Right? These guys drop, and now all I have to solve is the c prime of y is equal to 2y cubed. Exactly. Integrate both sides dy. On the left-hand side, we just get c of y. And on the right-hand side, 2y to the 4 over 4 plus some constant k or c or whatever you want to call it, which is 1/2 y to the 4th plus constant k. Bring that back to the function. Remember that the part up there, after the first integration, there was already a solution. All the extra we did was just to find that cy part. So now that I have a cy part, I can just copy the function. Phi xy is equal to 1/2 x to the 4th plus 1/2 x squared y squared plus, and instead of cy, now I have 1/2 y to the 4 plus constant k. Well, yeah, we don't know what, right? It could be plus 7 at the end. Could be plus minus 30. We don't know, right? Unless we are given some kind of initial condition to figure it out, just like in Calc 1. So the first constant you obtain is a function. Second constant you obtain is actually a constant, a number. It's not a function. Now, for those of you that are interested, whether you're doing problem right or not, you will obviously take the partial derivatives and make sure that when you do the gradient of that, you are getting this. Because the idea of the conservative vector field, I mean, the idea of the whole thing is to take the partial derivatives of potential function and create the vector field. This procedure was to go backwards. So quickly to review, when you have your vector field, you have your f and g, and you will run the procedure, the test for conservative vector field, and first verify that you have a vector field. If you have a conservative vector field, then you are guaranteed to have a function that generated that field. If it's not conservative, you could still have it, but it's not guaranteed. So, you know, your efforts might be wasted. So now that we know that this is a conservative vector field, then this has to be partial derivative with respect to x, this has to be partial derivative with respect to y, which is what I denoted at the bottom in red, and then you just follow from there. Take f, which is partial derivative with respect to x, and integrate in respect to x. What you get is already a solution, right? It's already the potential function. However, we have the function in the end as a constant function in terms of y, which we can still determine what it is. And the way to solve that is to differentiate your potential function, your new potential function, differentiate that in respect to y, and set it up to the y from the top, which is, the partial derivative y from the top, which is your g. From there, you will see what the c prime is. Integrate c prime, which gives you what the cy is. Plug that back in, and you have the answer. Now, I will encourage you to go home, right, and take the same problem and start this problem from g. So you find the integral of g in respect to y. You will get phi, which will have plus cx, right? And then differentiate in respect to x, set it equal to f, and then figure out what cx is eventually. It doesn't matter where you start. You can start from f, you can start from g. It doesn't matter where you start. It's just important to make sure you are using the right constants there. All right, so now that that is done, that was problem 14. Let's take a look if we can find something that has 3D. Let's take a look at problem 22. Okay. No yawning. Problem 22 in R3. So we have the vector field to be yz, xz, and xy. So these are your FGH. Now, just run all of the combinations and cross them, right? So you want to run, that's the way I remembered as a student, right? We have partial f, partial g. Now g has y assigned, right? That's the second one. So this is partial y, and this is partial x. And then we have partial f, partial z, partial h. So h is connected to z, so that's going to be partial z and then partial x. And finally, partial g, partial h, dz, and dy. All right, so what is my partial f, partial y? Partial f, partial y is just z. And partial g, partial x is z. All right, passes the first one. Partial f, partial z. Partial f, partial z is y. Partial h, partial x. Partial h, partial x is y. Y equals y. Good. Pass. Partial g, partial z is x. Partial h, partial y. Partial h, partial y is x as well. Pass. Pass. So I passed all three conditions. If only one of these fails, it's not conservative, right? You got to know your derivatives well. I mean, you know, you making a mistake on partial derivatives, right? Conservative fields don't care that you made a mistake, right? So make sure you do a good job there. All right, we have a conservative vector field. That means that my vector field F is actually del of phi, which is the partial derivatives, like vector of partial derivatives. Y in respect to x. And get xyz. Plus the constant in respect to y and z. There we go. Now, guys, this is already a solution, okay? It's a partial solution. I have my phi xyz to be xyz plus some unknown function in terms of y and z. I can lightly box this as a partial solution. We are not done. You know what has to happen. We are going to differentiate this in terms of the next variable. Let's pick y. So now, partial derivative in respect to y of the whole thing is going to be what? It's going to be xz, very good, plus, and now here is the new thing, partial c in respect to y. So you don't get to write now c prime, because c prime is the single derivative for a single variable. You have two variables now, x and y, so proper notation for that would be partial derivative of c. C is in terms of x and z, of y and z, right? And that's a partial derivative in respect to y. You will set that equal to your g, which is xz. Great. When you compare xz plus partial c partial y, that it's equal to xz, you quickly see that partial c partial y is equal to 0. Now you will integrate both sides in respect to y. So we will integrate partial c partial y dy equals to the integral of 0 dy, and what you get is that the function c, which was the function of x of y and z, is equal to 0 plus a new constant k in respect to z. Right? So that's usually, that's the issue for exams and things, so be mindful of that. Now, we bring this back to our problem and make the problem better. We have phi of xyz is equal to xyz plus, and now instead of having a function c of y and z, I'm having a function k in respect to z alone. Rinse and repeat. One more time for z. Partial derivative of z is going to give us xy plus, and here is the k prime, of z. It's a calc 1 now, one variable only, so we are allowed to put... Now, you can always write partial derivatives. You will never be wrong. You don't have to put prime ever. Every time you can just use partial derivatives. You can replace all of your derivatives in calc 1 with a partial notation. We don't need d notation at all. At all, right? We can just use the squiggly d. From calc 1 all the way forever. But, you know, whatever. We can use both. So now that we have this, we will set this equal to age, and age was xy. So when we have xy plus k prime of z is equal to xy, that tells us that k prime of z is 0. We are going to integrate k prime of z dz, and on the other end, integrate 0 dz. This tells us that the kz is equal to 0 plus some constant m, whatever. Now that m is a constant. It's not a function anymore. Over here you solved calculus 1 integral, and calculus 1 integrals have just plus c, which are just constants. So this capital M is just a calculus 1 plus c, which is a constant, whether it's a pi, whether it's 2, whether it's negative half, whatever it is. Great. Now I take that and I bring that back to my, remember we had the partial solution over here? So bring that back in a partial solution to get the overall solution for the problem. XYZ is equal to XYZ plus some constant m. You know what? I can just put, let's put m. I want to put c, but fine. And then that's what you box. Go ahead, take partial derivatives of this function. If you take the gradient, which is the partial derivatives, vector of partial derivatives, you will get your vector field. Partial with respect to x, first component yz. Yeah, flip 3 pages before we started the problem. And then the second component xz. And the third component xy, right? Just don't be lazy to check it on the exam. This is a guaranteed win, right? A problem like this could be 10, 12 points, right? Very easy to check. And if your function at the end, when you take partial derivatives, doesn't give the original problem back, then it's an issue. Did any of this make sense? Now, is anyone going into differential equations anytime soon? You are going, well, you already did this. Those of you going into differential equations, yeah, something that is called exact equations. Just different name, same procedure, all right? So you will be working out this problem over here. You will take the differential equation, write differential equation as the exact equation. You will have the same condition with partial derivatives. And those will, in differential equations, those will be called conditions for exactness. Because if those conditions hold, your equation is called exact equation, and you will unleash these steps to solve the differential equation. So if you're going in DiffEq, start problem 14, because that will be exactly the thing that you will be doing. One more thing remains. and that is to evaluate line integrals. Remember the line integrals from last time? I had a lot of stuff to do, parametrization, and then plug everything in, and then, right, have fun. Each problem was like 15 pages long. The goal of this section is to ease that up a little bit, and also the goal of the next section, which is Green's theorem, is also to ease some of the calculations up. So some of these work only in certain situations. You can't always use these methods. Calculating the line integral the long way works 100% of the time. But if you are integrating over a square, for instance, then your parametrization has the 4 separate lines, and you have to do 4 separate integrals, 4 line integrals, right? And we'll see on Wednesday that if you are using Green's theorem on something that it's on the closed curve, instead of having, you know, a page-and-a-half calculation of 4 separate integrals, so 4 separate line integrals, we can just do a one-liner using the Green's theorem. That's the purpose of the Green's theorem, but it will only work on closed curves. So now we are going to jump and learn something similar in here, and believe it or not, this is called fundamental theorem of line integrals. All right, 4 line integrals. So very important, right? Fundamental theorem for line integrals. Do you remember the fundamental theorem of calculus, which said that the way to compute the definite integrals? So let me just write over here real quickly. Calc 1, fundamental theorem of calculus, part 1, said that the integral a to b of f of x dx was any antiderivative f of x computed from a to b, which was capital F of b minus capital F of a. So this was the part 1 of the fundamental theorem of calculus, which states how to compute area under the curve if the integral is above x-axis. Now, for fundamental theorem of line integrals, we are going to write pretty much the same thing. I'm going to say that the line integral of the vector field, right, started with the unit tangent vector ds, which can be interpreted as the vector of fdr, that's our way to compute this, can be computed as phi of b minus phi of a. That is the fundamental theorem of line integrals. And this a and b are simply the points, whether we are doing this in R2 or R3. So a and b are points in R2 or R3. So if you go back to our lecture, you would see me, previous lecture, you would see me figuring out for line integrals, right? Figuring out the field, figuring out the R, the parametrization, then doing the dot product, then integrating, right? Everything took time. to compute this part. That was in 14.2, how to compute the line integral over the vector field. What this is telling me is figure out the potential function if f is conservative. And then just instead of doing all of the stuff for line integrals, just do a simple subtraction. Right? Remember what phi is, guys. Phi is a function of x and a y. That's what phi is. And a is a point, xy, say, I don't know, 3, 2. So, if you have phi to be given as x squared minus y, then your phi of a is 3 squared minus 2, 7. Do you understand what kind of calculation you are doing? You are doing basic arithmetic instead of calculus. It's a very powerful stuff. But it works only if f is conservative. Because if f is conservative in your vector field line integral calculation, then you have those potential functions. You will plug in the points at the end, right? Remember what the line integral was, the line that stretches between 2 points. We had an example in class that we did, a line segment which stretched from 0, 0 to 5, 5. Well, A is 0, 0 and B is 5, 5 in that example, right? So instead of parametricizing and going through all of this, whole page calculation, you will, in the potential function, you will plug in 5, 5, and you will plug in 0, 0, and you will subtract those two numbers at the end, and that's it. So there will be no line integral calculation. So that's the idea of fundamental general calculus. Instead of doing the line integral, you do arithmetic. Again, it works only if you have conservative vector field as f. If it's not conservative, then no potential function, and then forget about this. You actually have to go and do a whole page calculation for the line integral. Fair? We're going to have the same conditions, different conditions, but it's going to be the same idea for our next class. We will do the Green's theorem, and we will learn how to transform the line integral into calculation over the area, which is, we are going to transform your line integral into section 13.1, 13.2. All right, double integral rectangular region or double integral general region. So we are going to transform that, but then again, there will be some conditions that you will have to check before you can make the transformation from line integral into a basic 13.1 or 13.2 integral. And that's next class. See you all in 2 days.